Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the great stuff. This is the AAS Journal Author Series. And I'm super happy to have Ananya Bandopadhyay with us today. Hello, Anya.
Hi, Frank.
And Anya, where are you located? What's your geolocation?
So I'm at Syracuse University and I'm a third-year PhD candidate here.
Oh, very good.
So currently in a very snowy Syracuse.
Super. Well, it won't be too long before I get to say congratulations, Dr. Ananya. Very good. In Syracuse, it is January 22nd, 2024 as we record this. And is there snow on the ground in Syracuse?
There is, yeah. So there's no snowfall today, but we're expecting more snowfall tomorrow. And we have been through a few snowstorms already. So quite a lot of snow.
Good. Okay. I am in Phoenix, and we are definitely in our winter weather. In fact, we're getting a little storm rolling through, so we're going to have rain in Phoenix in the desert for about the next 3 days. This will make the spring flowers very happy when they get there. So it's all very cool.
Yeah.
Cool. And Ananya, what do you like to do for research?
Yeah, so my research primarily focuses on high energy astrophysical phenomena. And I've been studying tidal disruption events, which is also what we'll be talking about today in much more detail.
Cool.
So yeah, I like to study these through numerical and analytic methods to approach these events. Yeah.
Lovely. And I think we're going to see a little bit of that as we go to this very lovely APJ letter. It is open access. It's the open access era, people. Go grab a copy for free.
Yeah.
Peak of the fallback rate from tidal disruption events, dependence on stellar types. And Anya, take us away.
Thanks for reading out the title. And yeah, as we can see from the title, we're talking about the peak of the fallback rate in TDEs here and how this depends on stellar type. So to motivate the background behind this study and to describe what a tidal disruption event or a TDE is to people who are not used to thinking about this on a daily basis. So the main players in a tidal disruption event are supermassive black holes. And these supermassive black holes are very extreme objects. They have the mass of about 1 million times our sun or more, compressed into a very small volume. And by virtue of this, they have some of the most extreme gravitational fields that are conceivable in our universe, which also means that the gravitational fields of the supermassive black holes are so strong that they do not even let light escape. And so they are dark, or they emit no light of their own. So even though these objects are known to exist in our predictions of general relativity, they're very hard to observe.
Indeed.
But in certain scenarios, like the tidal disruption events being one such scenario, there is an external source of gas or fluid which lights up the supermassive black holes and allows us to observe these. So in a tidal disruption event, we have a main sequence star, something like our sun, come in very close vicinity to a supermassive black hole. And the tidal forces of the black hole, which are so strong by virtue of the fact that the gravitational field of the black hole is so strong, the tidal forces can tend to rip the star apart. And the shredded stellar debris from this disruption will then accrete onto the black hole and provide a brief supply of gas, which lights up the black hole and allows us to observe these. So TDEs are very important for their role in allowing us to observe supermassive black holes, which are otherwise so hard to observe. And so they have been studied since the very early, like 1980s. And at this point, I would also like to introduce our authors, actually. The authors of the study. So I said I'm a graduate student at Syracuse. And I did this work with my advisor, Eric Coughlin, and our collaborator, Chris Nixon, who's at the University of Leeds. And Julia is an undergraduate student in our group. Daniel and Matthew are graduate students in our group. And most importantly, Aluel, Valentino, Sarah, and Angela are high school students from the Syracuse City School District who worked with us in a summer research program that our department has been organizing for the last 2 summers. And this is called the Syracuse University Research in Physics program. So this was like a great opportunity for them as well as for us to interact with high school students and involve them this research. So a shout out to all of my co-authors.
Good.
So yeah,
Okay.
I think I've been through some of the introduction already in my brief discussion of TDEs. But what we are doing in this paper is we are talking about an analytic model that studies the fallback rate from TDEs.
Okay.
And the reason for, so this model is called the frozen in approximation. And the reason for coming up with these analytic models is that if you want to describe the fallback properties from TDEs very accurately, then the best way to do that is through numerical simulations. But the parameter space involved in TDEs, so the range of stars that can be disrupted by black holes, and also the masses and spins of black holes, is so large that it makes doing this extensive range of computational simulations very difficult. So it's always useful to have such analytic models.
Absolutely.
And the frozen in approximation, which is one such analytic model, has existed since the early 1980s. And is a very widely accepted model that has been used to study TDEs. So this model makes some crude approximations about the properties of the star. And one such approximation that it makes is that in order to completely destroy the star, what we have to do is we have to overcome the tidal field of the black hole has to overcome the gravitational field of the star. And that would create an imbalance between the pressure and gravity in the star and rip the star apart.
Yes.
So in order to meet this criterion of the gravitational field of the star being overpowered by the tidal field of the black hole, we use just GM over R square, which is essentially just the gravitational field of the star at its radius, where M is the mass and R is the radius of the star. And the condition that gives us this definition of tidal radius that we see in equation 1 is that we equate the tidal field of the black hole to the value of gravitational field of the star at its radius, at its outer radius. And that gives us this definition for tidal radius. And this is sort of like the distance that the star has to approach within the black hole, like the distance with close enough to the black hole, the star approaches. When the star approaches the tidal radius, we sort of assume that the gravitational field of the star is overpowered. And what the frozen-in model does is, up to this point, it assumes a perfectly hydrostatically balanced spherical star. And then beyond the point where the star reaches the tidal radius, we sort of magically remove the gravity of the star. And the constituent fluid particles of the star will then move in ballistic trajectories and accrete onto the black hole. So that is the gist of the frozen-in approximation. And this gives us a prescription for calculating the fallback rate and the time scale associated with fallback rate from the disruption of stars by supermassive black holes. So this model, like I said, has been around since the 1980s. And the early numerical simulations that people did since the 1980s were done with some toy models of stars using these polytropic stellar models. And these simulations were in reasonably good agreement with the frozen-in approximation. So this model continued to be widely accepted. Till we come to the era where people wrote these stellar evolution codes like MESA, one of the codes that I've highlighted here. And what happened with these is that now we could evolve stars given a stellar mass and properties of the star. We could evolve stars along their main sequence and then get sort of snapshots of these stars at different ages. And then, that's good. Okay. So the snapshots of the star that we can obtain from these stellar evolution codes like MESA can then be fed as inputs to hydrodynamical simulations. And that allows us to study the tidal disruption events for much more realistic stellar structures. And when people began simulating tidal disruption events for these realistic stellar structures, like we can see a few of these citations here, Golightly et al. In 2019 and Law Smith et al. 2019 and 2020. All of these works here basically took the next step forward by simulating realistic stellar structures using density profiles from some stellar evolution code like MESA. And what these simulations began to unravel was that there was a discrepancy in the prediction of the peak fallback time, which is obtained from the frozen-in model versus what we get from the numerical simulations. So the numerical simulations are believed to be, or are known to be the most accurate because they make the least amount of approximations about the ongoing physics and they just solve the equations of motion.
Right.
So this then puts to question the validity of the frozen-in model.
Okay.
And then also raises the question of, can we come up with a better analytic model that makes less assumptions or better assumptions about the ongoing physics and gives us a prescription to calculate the fallback rate without having to go through a huge, extensive range of numerical simulations.
Cool. I'm with you.
So yeah, this is where I am introducing the second analytic model that we are describing today. So this model was developed last year by my advisor Eric and his collaborator Chris. So this model is being called the CN22 model after their last names Coughlin and Nixon. And what this model does is that sorry, I think I lost the sound. Yeah.
All good. All good. You hear me?
Yeah.
Okay. Okay.
Yeah. So what this model does is that it challenges the prescription of the frozen approximation by saying that, first of all, the maximum gravitational field within a star does not occur at its surface, but somewhere interior to the star. And the reason that the way that we can think about this is that the gravitational field within a star is like a product of the density profile and the volume that you enclose as you go to larger and larger radii within the star.
Yes.
So yeah, right. So the density of the star decreases as we go to larger and larger radii, but then the volume enclosed increases. So there is some sweet spot within the star where the gravitational field is maximized.
Okay.
And what this model says that it is not just enough to overcome GM over R square by the tidal field of the black hole, but in order to completely destroy a star, we need to overcome this maximum value of gravitational field that occurs somewhere in the interior of the star. Right. Okay. So that's an improvement over the frozen-in model by accounting for the self-gravity of the star more accurately. And this then leads us to the definition of core radius, or capital RC. So this is the value of the radius within the star where the gravitational field is maximized. And then if we equate the tidal force of the black hole to the gravitational field of the star at this core radius, then we get a new condition for completely destroying the star and a new definition for tidal radius, which we are denoting as R subscript T comma C. I think that appears for the first time in equation 2 or maybe a little before equation 2.
It comes in a little before equation 2, but there's T peak. And this is RTC. Here we go.
So the RTC that we see here is this refined definition of critical tidal radius, within which the star must approach in order to be completely destroyed. So I just described how the CN22 model sort of improves over the frozen-in model by refining the approximations made about the process. And then using this model and following the prescription that was outlined in Loreto et al., which should be cited somewhere here. So Loreto et al. Was one of the early papers which calculated the peak fallback timescale from TDEs. And if we plug in the new definition of tidal radius and core radius into their equation, then we end up with equation 2, which gives us the peak timescale associated with the complete disruption of stars. So as we can see, it depends on the critical tidal radius, the core radius, as well as on the mass of the black hole, which appears in the square root of GM bullet. So this is the mass of the black hole. And we can also calculate the magnitude of peak fallback rate using the next equation. So the magnitude of peak fallback rate is being like sort of roughly calculated as m star over 4 T peak. And the the way to motivate this is that the total fallback of material that happens is about half of the star, because half of the disrupted star is actually gravitationally bound to the black hole. The other half is just released on a external, like an outward trajectory. But the half that is bound to the star will now accrete onto the black hole over some time scale. But then what this model suggests is by the time that the peak luminosity is reached, about half of this total material is accreted, which then gives rise to this factor of 4. And that gives us a closed form analytic expression that we can now use to calculate the peak fallback time scale and peak fallback rate for different stars. And now if we can go over to figure 1 of the paper, which is in the next page.
Let's take a look at figure 1. Okay, figure 1.
Yeah. Right. So I'm going to be talking about the left-hand side figure first.
Okay, let's
So
go over these are peak fallbacks. Let's zoom this in a little bit and M peak versus T peak. Okay.
yep. So like you just said, we have plotted here the peak fallback rate as a function of the peak time scale associated. And we did this for a bunch of stars that we evolved using MESA. So the stellar mass range goes from 0.2 to 5 because stars of masses much higher than this are much rarer in our universe. So this is like a very representative set of stars that we would expect to observe in TDEs. So we are also using snapshots of the star at 3 different ages, and these ages are indicated by the core hydrogen fraction remaining in the star. So zero age main sequence, or ZAMS, is when the star has just started fusing hydrogen in its core and has entered its main sequence.
Yes.
The middle age main sequence is an intermediate age that we chose based on when the star has about 20% hydrogen remaining in its core.
Okay.
And then terminal age main sequence is when the star has almost exhausted its supply of hydrogen and is going to go off the main sequence. And that is what we call as snaps. So if we, right, yeah. So if we take snapshots of the stars at these 3 different ages and use the frozen-in approximation to calculate the peak time scale associated with the fallback and also the magnitude of peak fallback, then what we end up with are these 3 lines, sort of horizontal lines that we see at the bottom. And we can see that the peak time scale, as we increase the mass of the star, shifts to later and later times and goes to of the order of 1 to 10 years for the very high mass stars.
Yeah.
And also as the stars age, which is if we go from top to bottom here, so the circle is zero age main sequence, the square is middle age main sequence, and then finally the rhombus is terminal age main sequence. So as the star ages, it also becomes more and more difficult to destroy the star. And the reason being that as the star ages, it's fusing hydrogen and creating helium in its core. So it develops a sort of more concentrated density profile. And so it's more difficult to destroy the star, meaning that this shifts the peak time scale to the right. And also the magnitude of peak fallback goes down a little bit as we encounter more and more concentrated density profiles. So the frozen-in approximation says that we have peak time scales which range from something like a few months or a few days to of the order of 10 years for this range of stars that we considered here. And the magnitude of peak fallback varies very little, but basically decreases a little bit for stars of increasing mass. And then subsequently has a very gentle rise for the high mass stars. And this is a technical issue related to the swap in the nature of radiative and convective cores and envelope structures of the star. So I'm not going to go too much into that.
Right.
But what is also important here is that the frozen-in model is not in very good agreement with numerical simulations. And to illustrate that further, I want to take you on a slight detour to figure 2 of the paper.
Absolutely. Figure 2 right down here. Figure 2. There we go. Bang.
Yeah. Thank you. So here I've shown the fallback rate for the complete disruption of a 3 solar mass zero age main sequence star by a 1,000,000 solar mass black hole. Yeah. So this is a reasonably high mass star being disrupted by a black hole. And the solid curve shows us the result of a numerical simulation. So this is supposed to be as accurate as it can get. And the dashed curve here shows us the prediction from the frozen-in model, which is the first early analytic model that we're talking about. So ideally, if this model was a good representation of the ongoing physics, then we should have got an overlapping or at least close fallback rate. But as we can see that at the peak, this model is discrepant by almost 2 orders of magnitude on both the X and Y axis. So both in peak time scale and in peak fallback magnitude. So this is clearly showing us that the frozen-in model is not in very good agreement with numerical simulations. And so we will now walk over to the other model that we're describing here, which is the CN22 model. And if you can go back to figure 1 again.
Yeah, you want to go to B or stay on A?
A is fine. I want to walk to B while going through A first.
Okay.
Can we go to A? Yeah. So yeah, so I described the frozen-in model points. And what the CN22 model gives us is this cluster of points, which is very tightly peaked around here. And the cluster of points here, obviously, we can see has very less variation. So I zoomed into this on the right-hand side of the figure.
Oh,
And
zoom in here.
Yeah.
I'm with you. Okay. Mhm.
Yeah. So this figure now shows us the prediction of the CN22 model on a linear scale. So
Right.
again, we have time to peak, but this is now in days. And on the y-axis, we have the magnitude of the peak fallback rate in solar masses per year. So
Man.
yeah, so we have used the same range of stars here and the same ages again.
Huh.
The only thing that's different, I mean, no, actually, there's no difference. You've just used the same stars as we used for the frozen end model.
Right.
So what we see here is that we can't really distinguish a very clear trend in the peak time scale. So there's a lot of intercrossing between the lines.
Yes.
But what is important is that all of these peak on a time scale of something between 15 to 35 days.
Right.
And the ones that I've made shaded in translucent here are the stars that we would not expect to observe within the age of our universe. So these have lifetimes which are much longer than 14 billion years. So we've just included them for the sake of completeness, but we wouldn't really expect to observe these translucently colored stars.
Right.
So all of these peak on a time scale that is very closely concentrated around 20 to 35 days. And the magnitude of peak fallback kind of varies linearly with stellar mass, which is easy to see from the equation that calculates this, because we had m star over 4 t peak as the peak fallback rate magnitude.
Yes.
So if t peak does not vary very much with stellar properties, then that basically means that this scales roughly linearly with the stellar mass, like the peak fallback rate scales roughly linearly with stellar mass.
Cool.
And what is also interesting is that we compared the results of these of the CN22 model with a bunch of numerical simulations that exist. So the SPH SAMs and SPH MAMs are a result of numerical simulations. SPH stands for smooth particle hydrodynamics.
Yes.
And this is a type of Lagrangian hydrodynamics code that is generally used to simulate TDs and to study TDs. So the inverted and upright triangles, as we see here, are color-coded the same as the mass of the stars, as the color code used for the mass of the stars here.
Okay.
So the fact that these triangles are so close to the points that they represent basically shows excellent agreement between the model and numerical simulations. And that sort of suggests to us that this model can have very important implications in the context of observations.
Okay.
So I think I'm good with describing this figure now. Cool. So I can walk over to figure 3, so the one after the fallback rates, for a little bit.
Okay, covered figure 2, that one good. There's our normalized probability. And figure 3, probability distribution functions.
Yeah. So we saw that the CN22 model predicted a very narrow range of peak time scales.
Yes.
But here we have just illustrated this further by plotting a histogram of the peak time scales associated with the disruption of these different ages of the stars, ZAMs, MAMs, and TAMs, as we walked over in the previous figure also. So,
okay.
And then the orange one shows the cumulative distribution. So the figure on the left is just the raw distributions of all of the stars that we considered in this study.
Yes.
And
mean peak. Okay.
Yeah, that gives us a mean of around 23 days and a standard deviation of around 4 days.
Okay.
But to tie this even closer with observations, we plot the next histogram, which is the figure on the right. So what this does is we take all of our stars, which we evolved for the study, and then we reweight the distribution of those stars with the present day mass function.
Okay.
So as we know, all stars are not equally abundant. So all masses and ages of stars are not equally abundant in our universe. So reweighting the distribution with the present day mass function takes us closer to the observed distribution of stars that we would expect or observed distribution of TDs that we would expect from these stars. And what this reweighted distribution tells us is that this peak time scale is very tightly peaked around 30 days. So we have a mean of 29.8 days. Yes. And again, a very small standard deviation of around 3.6 days, meaning that irrespective of the type of the star being destroyed, we get a peak time scale of the order of 30 days, which is and a distribution which is very sharply peaked around this time scale.
Yes.
Now, this time scale is determined almost exclusively by the properties of the supermassive black hole and does not really depend on stellar properties, as we saw. So
Yeah.
this now acts as a direct probe of the properties of supermassive black hole, which are otherwise so
Yeah.
hard to study because they, like I said before, they emit no light of their own. So the peak time scale from the complete disruption of stars can tell us or can act as a direct probe, which allows us to study properties of the supermassive black holes in our universe.
Beautiful.
Which I think is very cool.
Very beautiful.
So,
and I just want to take a look at this mass function. Okay,
yeah.
we have some power laws.
Yeah, so for the mass function, we use the specific form of the truncated Krupa IMF. There are other present-day mass functions which have been considered in literature, and we are actually discussing the implications of using these in the first bullet point in the conclusion.
Okay.
So I think I can now walk through the observational implications, which we have sort of outlined in the conclusion section.
Okay.
So going through the bullet points, the first one, 3.1, I think we have gone over further than I.
Sorry.
So yeah, I wanted to talk about.
Sorry.
Okay, no, that's fine.
I see what you're doing. I'm good. I'm good. Sorry.
Yeah, I'll come to the figure when we get to that
good.
particular section of the conclusion. So yeah. So the first bullet point in our conclusions and implications section is outlining the T-peak distribution and how this relates to the stellar mass function.
Yes.
So like I said, in order to obtain the previous histogram, what we did was reweight our raw stars distribution of stars with the Krupa initial mass function truncated at 1.5 solar mass. So this is a good representation for a present-day mass function, which has been used in other TDE rate studies, a few of which I've cited in here. But we can also consider the effect of changing this present-day mass function and studying the effect of like different types of galaxies. So one such distribution that we can use is the Krupa IMF truncated at 1 solar mass, which is basically representative of old type galaxies, because we know that high mass stars tend to die sooner. So if we truncate the distribution of 1 solar mass, then we don't really have that many high mass stars, which is representative of an old type galaxy. Cool. And what this gives us is a distribution that is even more tightly peaked around 30 days. So the standard deviation reduces further from the 3.6 days we saw for the earlier one.
That makes sense.
And then we also considered a third type of present-day mass function, which is just the Krupa IMF that includes all stars up to 5 solar mass. Yes. And that gives us a slightly wider spread in the distribution. But again, the peak time scale was basically the mean of the distribution was still close to 30 days. So the high mass stars would tend to cause a slightly wider spread. But the result that this peak time scale of 30 days is observed still holds up. And it has been observed that TDEs tend to occur preferentially in these young star-forming galaxies, which are called E+A galaxies. And so we would expect to see a representative population of high mass stars, which could cause a wider spread in this observed peak time scale of 30 days. But that does not change the result that we would be likely to observe this 30-day time scale. And that will help us study properties of the supermassive black hole, which are causing these TDEs.
Okay,
so now, yeah. So going over to the second point in the, to 3.2, how this peak timescale distribution depends on the black hole mass. So the black hole mass dependence comes in equation 3, which is T peak goes as somewhat like somewhere around 30 days, and it scales as the square root of black hole mass. So this is not a very strong dependence because it's the square root of black hole mass. But what this basically means is that if you're, so all of the disruptions that we were considering so far were being considered by a 1 million solar mass black hole. And for this, the peak time scale was around 30 days. Yes. But if we increase the mass of the black hole, this peak time scale increases to some extent. But there is a related caveat here that I want to point out, which is that if you have very massive black holes, which are more than a few times 10 to the 7 solar masses, then these black holes would have a very large Schwarzschild radius or a very large event horizon. Yes. So what they would tend to do is they would engulf the star completely, and there would be no observable TDE because anything that happens behind the event horizon is not going to be observed by external observers. So the black hole mass cannot be increased too much without just completely engulfing the star, which tells us that for all observed complete disruptions of the stars that we expect to see, we would get a peak time scale that would be peaked at something less than around 100 days. if
Right.
you allowing for the slight increase
Uh-huh.
with the increase in black hole mass.
10 to 7.
Yeah, we
Vector
just use
speed,
this equation and
vector days.
extrapolate.
Yep.
Yeah.
Mhm.
M to the power half, that gives us peak time scales which are less than 100 days,
Mhm.
which is great because then we can, if we see a light curve that has a peak time scale of something like 100 days, and then we also know how the late time scaling of these TDA light curves looks like. So these usually, complete disruptions usually go as t to the power minus 5/3, where t is the time. So if we see this late time scaling and observe a peak time scale, then we know that this is a complete disruption, and then we can infer the black hole mass directly from these light curves.
Right.
So yeah.
Cool. Very nice. Okay.
Yeah.
Right.
Right. And also we have pointed out here that this is actually in great agreement with the observed TDs, which were reported in this Hammerstein et al. Paper. So these were 30 TDs that they considered from the Zwicky transient facility, and all of these exhibited peak timescales of about 50 days. So that actually is in reasonably good agreement with the predictions of our model. So yeah, that's great. So in the next section, we have outlined the impact of partial tidal disruptions. So all this while I've been talking about a star being completely destroyed by a black hole, but there can also be situations in which a star comes close to a black hole, but not close enough to be completely destroyed.
Right.
So what then happens is that the tidal forces of the black hole will strip off some mass from the outer envelope of the star, and this mass will give rise to an accretion flare.
Yes.
But the light curve properties of these partial tidal disruption events will be slightly different from those of the complete disruptions that we were talking about. So yeah, one such example of how these differ is that the late time scaling goes as t to the minus 9/4 compared to t to the minus 5/3 in complete disruptions.
Right.
And also the peak time scale associated with these partial disruptions is not entirely determined by the mass of the black hole. So there is also dependence on how close the star comes to the supermassive black hole as it's on its orbit.
Right.
Because if you're not destroying all of the star, but just stripping off a fraction of its outer envelope, then how close it comes to the orbit also determines how long it takes for the debris to fall back and accrete onto the black hole.
Agreed. Cool. Yep.
Yeah. So now we discuss the impact of partial disruptions on these observed light curves. So so partial disruptions are much more likely to occur for evolved and high mass stars because, like I said, these have a more concentrated structure. And the parameter that decides whether a disruption will be partial or complete is this critical impact parameter, which we have defined as beta, which is the ratio of, or beta critical actually, sorry. So this is the ratio of the classical tidal radius RT that we defined in the first equation, and also over the critical tidal radius RTC, which comes from the CN22 model.
Yes.
So yeah, as we have a higher mass or a more centrally concentrated, more evolved star, the critical distance within which the star has to approach in order to be completely destroyed becomes smaller and smaller. So the value of RTC decreases, or it becomes more difficult to destroy a star like this.
Right.
So the value of beta C increases. So we have plotted a distribution of beta C in figure 4. So going over to that.
Let's go to figure 4. Wrong way. Figure 4.
That should be just above that page, actually. Like,
okay, here we go.
Yeah.
Beta. All right, let's do global and zoom in. AB. Okay.
Right. So this shows this critical impact parameter as a function of stellar mass. Actually, the way that it is now is perfect because these two figures are sort of very interconnected.
Okay.
So the figure on the left is showing the critical impact parameter as a function of stellar mass for the different stars that we considered in the previous figures also, the zero-age main sequence, middle-age main sequence, and terminal-age main sequence stars.
Okay.
So the zero-age main sequence stars are the ones with the least concentrated stellar structures. So they have the lowest values of critical beta. This is the line here. So they are the easiest to destroy. And then as the star ages, it develops a more and more concentrated core and becomes more and more difficult to destroy. So these are the middle-age main sequence and terminal-age main sequence stars.
Okay.
Also closely related is this figure on the right, So what this is showing us is the distribution function of betas as a function of stellar mass. And we have defined this distribution function in an equation later, but it's not super important to go into the definition. What this is basically showing us is,
There we go, right?
This was the definition. So what this function is basically showing us is how probable is a star being completely disrupted, given that it enters within the loss cone. So when a star enters the loss cone or is going to be disrupted by a black hole, by the supermassive black hole, how likely is it to get completely disrupted versus just causing a partial disruption?
Okay.
So what this figure is showing us is this distribution function, f beta, and we go to the figure again.
And that is on this axis. Okay.
Right. Yeah.
So let's just do some limits. So this thing is 0.
Yeah.
Its distribution function is 0. What does that mean?
So yeah, if the distribution function is 0, then the star would not be completely destroyed ever. It would always be partially disrupted.
Gotcha.
So that would be if the tidal radius of the star were at the Schwarzschild radius of the black hole.
There we go. And if f of beta is 1, it's always disrupted.
Right, exactly. It's always
okay. Yeah, gotcha. Okay.
So we have plotted f of beta as a function of stellar mass and age. And what we see here, as expected, the zero-age main sequence stars are the most likely to get completely disrupted because they have the lowest values of beta and they are easiest to destroy. So this line of stars at the top gives us the zero-age main sequence stars, which would be the most likely to be disrupted. And then as the star ages, you obtain a more and more centrally concentrated density profile, and it becomes more and more difficult to completely destroy the star. So what this figure then suggests is that high mass and more evolved stars are much more likely to give rise to partial disruptions rather than complete disruptions. So it is important to note the impact of partial disruptions in these observed light curves. So not all TDEs that we observe are going to be complete. So we can't directly interpolate or extrapolate our results to partial disruptions. So it's just important as a caveat here to point out that a lot of the high mass stars are actually going to give rise to partial disruptions.
Big, massive helium core. Very cool. Nice. Makes sense. Very good.
So yeah, I guess that was all for this section. So the next observational implication that we have is again in the context of partial disruptions, but specifically long duration TDEs. So there have been these few sources like the GSN 069 source and the related papers that are outlined here. So these are very long duration sources. This particular source had an 11-year long light curve, which was initially explained as the complete disruption of a high mass star. Because as we saw, the frozen-in model tells us that if you have a high mass star being completely destroyed, then you can get light curves that peak on a time scale of 10 to 15 years.
Yes.
But what our model is showing us is that this is wrong. Obviously, we showed that high mass stars being completely destroyed are also not going to give rise to such long peak time scales. They're all going to be peaked around 30 to 50 days, unless the disruption was partial. So the only way that you can actually obtain a TDE light curve, which extends to 11 years, is if the disruption was partial. And then more recently, Minuti et al., the authors of these papers, wrote another paper which shows that the light curve from GSN 069 actually does show T to the minus 9/4 decay, which is the characteristic decay for a partial disruption. And so that, again, provides evidence to support the claims of our model that the only way that you can describe TDE light curves, explain TDE light curves as being years or 11 or more years long is if the disruption was partial. So that's an added feather on the hat of our model.
Bonus points.
Right. And then finally, we come to the context of jetted TDEs. So we don't always observe jets. Jetted TDEs are actually a very rare phenomena, and only a few of these have been observed. And people don't really understand very well what the driving mechanism for launching these relativistic jets is. But it has been proposed that these are probably related to super Eddington accretion rates, because when you have extremely super Eddington accretion rates, these can be responsible for driving winds off the accretion disk and giving rise to jets. So you need very high accretion rates in order to drive jets in TDEs. And then what our model tells us that the highest accretion rates or accretion luminosities would likely to be observed from the complete disruption of high mass stars. As you increase the mass of the star, the peak luminosity increases.
Right. Yes.
So the fact that jetted TDEs are rare, we are sort of correlating or trying to explain this as the intrinsic rarity of high mass stars in our universe. Because as we know, high mass stars are, they live shorter durations, and they're also intrinsically more rare in the initial mass function of stars.
Yes.
So there could be a possible correlation between the rarity of jetted TDEs and just the intrinsic rarity of high mass stars in our universe.
Okay.
And then another very important observational implication of this is that if so for the jetted TDEs that are observed, if we do a post-observation follow-up of the host galaxies of these, then these are likely to be observed, or these are likely to be coming from young star-forming galaxies, because these are galaxies where we would still have high mass stars that can be disrupted, giving rise to these. And lo and behold, if we look at the at the host galaxies of these few jetted TDEs that were observed, which is the last paragraph here, the Swift J1112 and 802022 CMC, these actually show properties that suggest that these do come from young star-forming galaxies. Yes. So again, our model is providing sort of an explanation or sort of a correlation for the emission mechanism in jetted TDEs and the host galaxies of these events. And finally, we have just outlined some of the most important observational implications of this model. And these include that the peak time scale for associated with the fallback rate and complete TDEs are roughly independent of stellar structure, and they are primarily determined by the black hole mass and scales as black hole mass to the power half. The only way that we can explain long duration light curves as coming from TDEs is if the disruption is partial. Complete disruptions are not going to result in decades long outburst, which have sometimes been explained as complete disruptions. Yes. And finally, the highest accretion, super Eddington accretion rates are likely to be the driving mechanisms for relativistic jets in TDEs. So using this, if we do follow up of host galaxies for TDEs, then we see this also is upheld by observations. We see that the host galaxies of TDEs are likely to be young star-forming galaxies where we have a lot of high mass stars that can get disrupted. So that comes to the end of our paper.
Awesome. Awesome. Very nice work.
Thank you.
Ananya, I want to thank you so much for walking us through your very lovely APJ letter. Very nice.
Thank you.
And you touched on it a little bit there, or at various points, and so let me just push on it a little bit. Where do you think we go from here, given the published article? Is there other stellar parameters that might be of interest? For example, just making this up, metallicity. Things along those lines. Are there other observational searches that could be done, et cetera? And just sort of next steps, where do we go from here, given the published article? Yeah,
I think the most obvious next step would be to see if this model actually matches the entire parameter space of stars that we are considering here. So like I said, I showed you a few comparisons of numerical simulations that exist in literature. But in order to be able to use these models for observations, we need to do a more exhaustive study of numerical study of disruption rates from stars. And that is what we are currently working on. And these MESA-generated profiles take care of metallicities and composition of stars. So yeah, they could provide additional observational constraints also, which will help strengthen our model in the future. So we are currently working on a related project that looks into that.
Very nice. Cool.
Yeah.
Oh,
sorry, I am in a shared office, so there might be a little bit of noise.
Where'd that come from? Okay.
So,
very cool.
Yeah.
Well, I really look forward to seeing this develop a little further on as you do some of those additional calculations on the SPH and tune that into different compositions. It'll be be nice to see this development. Very good. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.